When people try to explain the difference between an aircraft built by Boeing and an aircraft built by Airbus, the conversation almost always starts with the obvious visible stuff. One manufacturer's airplanes have a yoke, a kind of control wheel that looks and feels a bit like a car steering wheel, while the other manufacturer's airplanes feature a side stick, a compact joystick-like control mounted to the side of the pilot's seat. A Boeing airplane's thrust levers often physically move when the auto throttle system is engaged, while an Airbus airplane's thrust levers tend to remain stationary in preset positions, with the engines being controlled electronically. But if those visible differences are just the surface details, then what lies beneath? The technical, philosophical, and operational differences is what truly separates these two families of aircraft and their designers' approaches to piloting, automation, and safety. At its core, the Boeing versus Airbus distinction is not about appearances, but about control philosophy. Boeing grew up in an era dominated by mechanical linkages, cable runs, torque tubes, and direct pilot-to-surface connections. This engineering heritage shaped the belief that pilots should feel the airplane, that they should have tactile feedback from the aircraft, and that automation should assist rather than override human input. Airbus, by contrast, began development in a later era when digital computers were powerful and reliable enough to serve as real partners in controlling flight. Airbus embraced that technology, believing that computers could reduce pilot workload, prevent human errors, and enforce safe responses when the aircraft approached unsafe limits. This difference in philosophy pervades almost every system on their airplanes, from the way failures are presented to pilots, to how much authority pilots retain in emergency situations, to how the flight controls interpret a pilot's input. It shapes what pilots are taught in training, how they respond to abnormal situations, and how the aircraft itself responds to external forces. Perhaps the most visible introduction to this philosophical divide comes the moment a pilot steps into the flight deck. In an Airbus airplane, beginning with the A310 and refined through the entire A320, A330, A340, and later models, the cockpit follows what is known as a dark cockpit philosophy. In this approach, systems that are functioning normally do not draw attention at all. Buttons, switches, and indicators remain unlit when everything is operating as intended, and only illuminate when there is something that requires attention. This streamlines focus. The absence of lights is information. It tells the pilot that the airplane is configured and functioning as expected. Airbus crews commonly refer to all white lights out as a confirmation of a correctly set up airplane before departure. Boeing takes more explicit route. In most Boeing cockpits, including the 737 family, the 777 family, and earlier wide-body models like the 747 and 767, system switches are usually accompanied by illuminated indicators showing their status, whether on or off. These indicators do not disappear when the system is normal. Instead, they provide continuous confirmation of system states. Where an Airbus cockpit intentionally minimizes visual signals until something needs attention, a Boeing cockpit presents those signals continuously. This difference reflects a deeper contrast in how information is presented to pilots and how designers anticipated pilots would manage cognitive workload during flights. The divergence becomes even more pronounced when something goes wrong and the airplane has to communicate a failure to the crew. On Airbus airplanes, that job falls to the Electronic Centralized Aircraft Monitoring System, ECAM for short. ECAM constantly monitors hundreds of system parameters and, when a failure is detected, it not only alerts the pilots, but also guides them through the response with a prioritized, automatic step-by-step procedure displayed on the screens. The moment ECAM detects, for example, an engine anomaly, or a pressurization fault, it presents the crew with exactly what needs to be done. As each corrective action is completed, ECAM senses that and removes or updates the checklist item automatically. The system essentially becomes a real-time partner in diagnosing and resolving the event. Boeing aircraft use a different system called the Engine Indicating and Crew Alerting System, or ECAS. Like ECAM, ECAS provides alerts and displays engine and system status information, but it does not automatically generate the associated non-normal checklist in the same interactive way that ECAM does. When ECAS displays a message, such as Generator 1, fail, or Fuel pump aft left fault, it is still up to the pilots to locate the relevant procedure, interpret the situation based on their training and experience, and carry out the actions. Boeing does offer electronic checklists that can be accessed by the flight crew on display units, but these must be manually selected. There is no automatic sense and do progression tied to each alert. The contrast here is not trivial. Airbus assumes humans are brilliant at higher-order decision-making, but fallible under stress. It uses automation to reduce cognitive workload and standardize response. Boeing assumes humans are central to decision-making and should always retain primary authority, with automation serving as an assistant rather than a director. The end goal, safety, is shared, but the route taken to get there reflects very different perspectives on how humans and machines should interact in the cockpit. This interplay of control philosophies becomes even more evident when we explore fly-by-wire systems and flight control laws. Fly-by-wire refers to flight control systems in which pilot inputs are converted into electronic signals that are interpreted by flight control computers and then sent to actuators that move the control surfaces. Neither Airbus nor Boeing uses the old mechanical cables and rods for primary flight controls on their modern airliners. But the way they interpret pilot inputs differs significantly. Airbus pioneered digital fly-by-wire in commercial aircraft with the A320 family. In an Airbus, when a pilot moves the side stick forward or backward, the system does not directly deflect the elevators in proportion to that movement. Instead, the pilot is requesting a desired aircraft behavior, typically a change in load factor or pitch, and the flight control computers determine how to move control surfaces to achieve that behavior safely. In normal operations, this means the aircraft maintains the commanded pitch or bank attitude indefinitely unless the pilot changes it. The aircraft does not automatically seek to return to a trimmed speed or attitude when the controls are released. Instead, automatic trim continually adjusts in the background so that the aircraft remains stable and balanced. Boeing also uses fly-by-wire technology, most notably on the 777 family and later models. However, Boeing's implementation retains what is known as artificial speed stability. When a pilot releases the control column on a Boeing airplane, the aircraft tends to return toward its trimmed state much like a traditional mechanical airplane would. Manual trimming, adjusting control surface bias to maintain a stable attitude, remains an important part of Boeing's piloting philosophy. A pitch change requires explicit trim input from the pilots to establish a new baseline. As such, Boeing airplanes feel more like conventional airplanes to pilots transitioning from older designs. This difference in speed stability illustrates a deeper truth. Airbus designs its control laws around consistency and envelope protection, while Boeing designs its systems around predictability and pilot feel. Airbus effectively removes certain natural aerodynamic tendencies, such as speed-related pitch changes, because its automation can manage them more efficiently. Boeing preserves those tendencies, but augments them with computerized assistance. When you look at roll control, how the aircraft banks left or right, Both manufacturers have integrated protections that reduce pilot workload. In a conventional airplane, banking increases the load on the wings and causes altitude loss if not countered with elevator input. Modern Airbus and Boeing fly-by-wire systems automatically compensate for this up to a point, allowing the aircraft to maintain altitude without the pilot having to pull back on the controls. Airbus typically provides this compensation up to a bank angle of about 33 degrees, while Boeing provides it up to about 30 degrees. Beyond these angles, Airbus introduces positive spiral stability, gently guiding the aircraft back towards safer bank limits if the controls are released, whereas Boeing allows the aircraft to remain at the selected bank, placing responsibility for attitude control more fully with the pilot. Delving deeper into Airbus specifically, Airbus aircraft operate under a system of control laws that define how pilot inputs are interpreted and what protections are active at any given time. In the most common mode, normal law, pitch commands are interpreted as load factor demands. When the pilot moves the side stick forward or backward, the system interprets that as a request for a certain number of GEs and moves the elevators accordingly. In roll, the side stick commands bank angle rather than direct aileron deflection. The flight control computers constantly adjust control surfaces and trim to maintain these commanded attitudes. Importantly, normal law includes flight envelope protections that actively prevent the aircraft from stalling, overspeeding, overbanking, or exceeding maximum pitch limits. These protections help ensure that the aircraft remains within safe operating parameters. If certain failures occur, for example, significant sensor discrepancies or multiple system faults, the aircraft transitions into alternate law. In alternate law, some protections are lost, but the airplane remains stable and responsive. There is a sequence. In the first level of alternate law, limited speed protections may still function. In the second level, only basic load factor protection might remain. If the aircraft degrades further, it enters direct law. In direct law, there is a direct relationship between the side stick movement and control surface deflection. Trimming must be performed manually because automatic trim is no longer available. A message such as "Use manual pitch trim" appears on the primary flight display to remind pilots of this change. In direct law, the airplane behaves more like a traditional aircraft without envelope protections. Boeing's control system degrades differently. Boeing aircraft also transition through modes such as normal, secondary, and direct, but the architecture is distinct. In Boeing airplanes, pilot inputs are first processed by actuator control electronics before being verified by primary flight computers and then sent back to actuators. In normal mode, Boeing aircraft behave much like conventional airplanes, with pitch commands directly affecting elevator position and manual trim remaining necessary. In secondary mode, protections are lost, and handling becomes more conventional but simplified. In direct mode, control signals are passed directly from the pilot to the control surfaces, bypassing most of the computing layers. A crucial difference in control law philosophy is that Airbus flight envelope protections in normal law are hard limits. The pilot cannot exceed them under normal conditions. Boeing's equivalent protections are soft limits. They resist but do not absolutely prevent exceedance. For example, if a Boeing airplane approaches an overspeed condition, the controls become stiffer and the pilot must apply extra force to exceed safe limits. Airbus, on the other hand, prevents the airplane from exceeding those limits altogether unless protections are specifically turned off by the system under certain degraded conditions. This distinction is often misunderstood in public discourse. Critics of Airbus have claimed that pilots lack authority to exceed protections, but in reality, Airbus protections are designed to deactivate automatically when the aircraft's systems determine that they are no longer reliable or that the situation requires direct pilot control. In contrast, Boeing allows pilots to apply additional control force to override its soft limits even in normal mode, but doing so relies on pilot judgment and strength. Another striking difference between Boeing and Airbus cockpits lies in the tactile connection between pilots. Boeing aircraft generally feature interconnected control columns. When one pilot moves the yoke, the other pilot's yoke moves in sync. This design mechanically reinforces crew coordination. The right seat pilot can feel what the left seat pilot is doing, and vice versa. Airbus does not interconnect its side sticks mechanically. Each side stick is independent. When both pilots apply inputs simultaneously, the system uses priority logic to determine which input is active, and visual or oral alerts inform the crew of dual input conditions. Airbus compensates for the lack of mechanical feedback with system logic and clear procedural communication cues. Throttle control is another area where the two philosophies diverge. In many Boeing aircraft, such as the 737 and 777 families, the auto-throttle system physically moves the thrust levers to the commanded setting, providing tactile feedback to the pilots. In contrast, Airbus thrust levers remain fixed at selected detents when auto-thrust is engaged, and the engines are controlled electronically. Airbus designers argue that engine instruments should be the source of information about thrust changes, rather than moving levers that could distract pilots. Both systems have their merits. Boeing's physical movement provides intuitive, tangible confirmation of thrust changes. Airbus's fixed levers simplify the control landscape and encourage pilots to monitor dedicated instrument displays rather than relying on mechanical movement. Beyond these core systems, smaller differences exist in areas such as speed brake behavior, flap modulation logic, and how autopilot and autothrust interact with the flight director. Boeing often preserves a more conventional feel, while Airbus emphasizes integrated automation and seamless transitions between manual and automated control. It would be easy to interpret these differences as a competition between two rival philosophies that cannot coexist. In reality, however, both manufacturers have borrowed ideas from one another over time. Modern Boeing cockpits increasingly incorporate automation features once thought exclusive to Airbus, and Airbus designs have become more flexible in accommodating pilot authority where necessary. The trade-offs between human control and automation support continue to evolve as avionics, processing power, and flight safety research advance. Neither Boeing nor Airbus expects pilots to relinquish responsibility. On the contrary, both manufacturers rely on highly trained professional flight crew members to make context-sensitive decisions in ways that computers cannot. The differences lie in how each system supports those decisions and manages risk. Ultimately, the question of which philosophy is better has no absolute answer. Much like the question of whether a person prefers a manual or automatic transmission in a car, the answer depends on context, training, and individual preference. Airbus aircraft provide a highly structured environment with extensive protections designed to reduce workload and prevent common errors. Boeing aircraft preserve a more tactile, traditional flying experience that many pilots find reassuring and intuitive, particularly those trained on earlier generations of airplanes. In the end, the safest airplane is not defined by its manufacturer, but by how well that airplane's systems are understood, anticipated, and respected by the pilots who fly it. Boeing and Airbus have both pushed the boundaries of aviation technology, learning from each other and from decades of operational experience. Their differences do not represent opposing universes, but rather complementary approaches to the same fundamental goal: getting passengers and crew safely from one place to another. The story of Boeing and Airbus is not one of simply yokes versus side sticks, or moving throttles versus fixed levers. It is a story of how humans and machines share the responsibility of flight, how trust is negotiated between pilot and computer, and how two engineering cultures, separated by geography and history, arrived at two different but equally successful ways of teaching an airplane to fly.